N700?
No, this is the, I forget the exact number. It's like the S45 or something like that. Yeah. It'll be useful, I promise.
Is that just like a review of 105?
No. You'll see stuff that you probably haven't seen before. So.
It's ungodly trying to find a hat.
It's like down in the basement.
Oh, I went up. It's my mistake.
I think this is like one of those buildings from like back in the day when like girls weren't allowed to go to school. So like there's only like one bathroom for the guys and like everyone's there. It looks like Donna Lab is like that too. You gotta go to like the third floor to see one bathroom.
I went to the third floor and then the men's bathroom was tight.
I think that's actually the back. I think that was.
The lone brave soul, huh?
That's a pretty nice bathroom.
As long as you make sure there's ice on the food.
I'll give people another minute or so. Yeah, those are lecture notes. So. All right, why don't we go ahead and get started. All right, so welcome to lecture number 5 of EE 141. So I'm obviously not Professor Rabai. He unfortunately couldn't be here due to a family emergency. So the schedule for the next couple weeks is going to be a little bit strange. So obviously there was no lecture this Wednesday, Today it's me. I'm Professor Aladalan, one of the new faculty here at UC Berkeley. I taught this course last semester, so it should be hopefully still pretty fresh for all you guys. Next Wednesday will again be no lecture. That'll be moved to a later time. Next Friday, one of Professor Urbai's students, who I believe is one of your GSIs, Simone, he'll be giving the lecture then. And then obviously there'll be a bunch of makeup lectures to cover all the material that we're sort of slipping by in a little bit. In terms of the labs, I think you guys should basically be done with lab number 2 by this point. Lab number 3 will be held next week. And I guess based on the attendance, maybe a bunch of you guys are still working on homework number 2, which I believe is due today. In terms of the next homeworks, I think one of the GSIs will make an announcement on sort of when those will go out, when they'll be doing all that. But homework number 2 is indeed due today, so if you're here and you haven't turned it in yet, I guess you can go run out afterwards. But otherwise, you'll be watching this, I guess, later on online. So any questions on kind of administrative types of things? Well, lab 1 was homework 1. So lab 2 is what's called, the first time you're actually in the lab. Other questions? Yeah, so definitely keep going on to the web. Just, there's obviously been changes with scheduling and everything like that. So keep checking in the website to make sure you're kind of up to date with what's going on. So with that, I think we can launch into the class material. So I think last time Jan talked about sort of design rules and maybe a little bit about CMOS manufacturing, and then started talking a little bit about just sort of what is the MOS transistor. So today we're going to go into a bit more detail on sort of how we're going to really model the transistor. Now, the reason we're doing this is because it's going to turn out you can actually use these models to understand a lot of trade-offs about CMOS gates in terms of their delay, their power consumption, how they scale when you move from one technology to the next, and all kinds of things that you really are going to be pretty interested in as a digital circuit designer. So it's not that you need to know every last little detail of what the electrons are doing, but we do want to have some relatively simple models that we can use just to understand the behavior of our circuits. So today it's going to be kind of the in-depth modeling part of it, but you'll see that we'll be making use of these models repetitively throughout the entire semester. Okay, so last lecture I think Jan ended up with essentially sort of treating the MOS transistor as a switch, and we said there was this sort of magic voltage at which the switch turned on, which we called the threshold voltage. So I believe Jan talked a little bit about sort of what the threshold actually is, but let me just kind of do a brief review of the concept just to kind of level set everybody. And again, if you have any questions, just feel free to stop me at any time. Just remember to use the microphones. So we said that if we're just going to treat our transistor as being a switch, and we just draw sort of our standard symbol, and we said if the VGS is less than the sort of magic VT, then the switch is just not conducting. And if the VGS is greater than this magic VT, then we said the switch is going to be closed with some on resistance here. So just sort of from a device standpoint, the way this works is that, well, normally the way we build the transistors, we've got an N+ junction for the source and for the drain. And then we have just the P substrate for sort of the body terminal. And then some piece of usually polysilicon for the gate with this oxide in between them. So normally if I have no, let's say, gate to source voltage here, well, I've just got sort of 2 PN junctions. So there's kind of no way I can conduct current through there, right? So we say that nominally it's the switch is off. So there's no current flowing through there. Well, so as I start increasing the gate voltage relative to the source over here, I'm going to attract some electrons up to the surface here. And once I've attracted enough electrons to do what's called inverting the type of this silicon here, normally it's p-type, and if I attract enough electrons, it's as if it's now become an n-type. Well, I just have this sort of conductive channel between the source and the drain, and now it's as if the switch is on. Okay? So what we're going to call this kind of magic voltage at which we get enough electrons here to invert the type, that's what we're going to call this threshold voltage. Now you can imagine that when we talk about this threshold voltage, it's not that things exactly happen, all of a sudden the switch just turns on right at that voltage, but that's a reasonable approximation, at least for what we're going to be talking about for today. And later when we talk more about power, we'll talk about kind of what's the real behavior looking like when you're kind of below this magic threshold voltage. So given that we've just defined this threshold as being the voltage at which the type of that silicon down there is inverting, you can imagine it kind of has to do with how much charge is there in that silicon to begin with that needs to be sort of mirrored to become now the n-type instead of the p-type. And so the kind of the details here of this equation are not super important. They have to do with essentially some material parameters and band gaps and things like that. If you want to kind of learn or remember more about that, I definitely encourage you to go and take a look at 105. But for this, it's really kind of not too super critical. The most important thing is that we're just trying to mirror some charge to get this thing to invert the type. Now, there is this gamma thing over here, which is called the body factor. What that has to do with is just, here I was always talking about the gate to source voltage. But really, there's this substrate here. And what happens is if you change the potential of this substrate relative to the source junction, well, this little depletion region thing that we're drawing here changes in width. And so when it changes in width, you have to image more charge in order, well, if I, let's say, increase the width, I have to image more charge in order to invert the type of the surface. And if I make the depletion region smaller, then I have to image less charge. And essentially what ends up happening is that the threshold voltage ends up changing. Now, this is not a usually super critical effect. It's just, I'm mentioning it here because it's important just to know that this is going to happen. So for example, if you have an NMOS transistor where let's say you're doing kind of the thing that we normally don't want to do, where let's say you're passing a high voltage through it, unless you have VDD over here, you just need to keep track of the fact that the threshold here is actually not going to be this, whatever the VT we tell you. I think in this process, it's probably something like 300 millivolts or so. Well, if you actually did something like this, the VT is going to be higher than that, maybe like 350 millivolts or 400 millivolts. Okay? So now that we kind of have this on-off behavior, we want to understand a little bit more detail as to, well, okay, the thing's not just on and off, right? There's some resistance associated with this conductive channel that we're forming here. So what we're going to do next is just kind of walk through the classic transistor derivation of what does the current actually look like as you start changing these terminal voltages here. So the first thing, the first experiment is, well, we've already put a positive VGS onto the transistor. So we have some charge underneath here. Now I'm going to start putting some VDS across the device, and I just want to see how much current is there going to be flowing through here. Okay? So before I kind of dive into the details, there's kind of one really important concept to remember here in terms of transistor currents. So anytime you have current in a device, particularly in a MOSFET, there's basically two terms that you need to keep track of. The first one is just how much charge do you have available here underneath the gate for current to flow with, right? Because remember, current is just charge per unit time. So if I've got more charge underneath there and it's moving, then it's essentially I've got more current, right? Now, the other piece of this that you can kind of just almost intuitively understand from what I just said is, well, having a lot of charge is good, but the other thing that's really good is for that charge to be moving really, really fast. Because I have to cover a certain distance, right? So the faster my charge is moving, the more charge I'm going to see flowing through from the source to the drain if it's moving more quickly, right? Now this analogy is, almost directly from like water flow, right? So if I give you like a pipe and I tell you that there's more water in that pipe, you'd obviously say, okay, well, I can get more water per unit time. And the faster that water is flowing, again, the more water per unit time you're going to get coming out of there. Okay? So if nothing else, and I'm going to write the sort of final equation first and then come back to the other ones, you should always remember that the current is essentially the charge times the velocity that charge is moving. Okay? Now, in this derivation that we're doing here, I'm always looking at sort of a slice of the transistor. So if you remember from sort of the layout view, this maybe is the piece of poly. And then here's maybe the source and the drain. So when we're doing these derivations, we're always looking at essentially a slice in that plane. Okay? So the only extra thing we have to add on to here is that, of course, the wider I make that transistor, the more sort of per unit, or more current I'm going to get, because this is really just the sort of per unit width metric that we're working with. Okay? So now to really get sort of an equation for this drain current, all we've got to do is essentially come up with what is the charge and what is the velocity. Okay? So let's start out with a charge. Well, So we said that I just have this sort of piece of poly with an oxide underneath it. And then essentially on the other side, there's this sort of body terminal, right? And then I've got the source over here. This is N+, and this is just grounded. This is also N+. So this looks kind of like a capacitor, right? So who remembers what the sort of, if I told you I have a certain capacitance C, how much charge is there in that capacitor? Who remembers that? Exactly, Q equals CV, right? Well, it turns out you can do almost this exact same thing. So I'm going to say that the Qi, now this Q is going to be a function of where in the channel we're looking. Because as we'll see in a second, the voltage in this direction is going to be changing. So just from a sort of notation standpoint, I've called this thing V of X here. That's not going to be a constant voltage. Because you can see we're going from the drain down to the source. So we're going to be dropping some voltage along this channel here. Okay? So what that's going to say is that the charge is going to be the Cox, and I'll define what the Cox is in 1 second. Well, the voltage on this top terminal over here is VG, and I'm just sort of implicitly calling the source as being ground, but you can call this as now being VGS. Okay? And so if I want to look at any individual point here, if this is, let's say, the x-axis, then now the voltage across the oxide there is just VGS minus whatever that V of X actually is. Okay? Now there's just one additional little thing that I have to add in here because of the fact that this is not really a linear capacitor. It's a MOS capacitor. So with a MOS capacitor, we said that we had to pull some number of electrons up to the surface before the thing really started conducting. Well, that number of electrons is just represented by that VT that we had just talked about. So the only last piece that I'm going to add into this equation over here is just that now the charge is not just C times the voltage across the capacitor, but C times that voltage minus this magic threshold VT. And this magic threshold, that's just representing how much of the charge I have to sort of image to begin with before I could get any conduction at all through this transistor here. Okay? The other thing that I didn't define, this Cox, that's just epsilon, the permittivity of the oxide, divided by the thickness of that oxide. So that's just that dimension right there. Okay? And that's just your standard capacitance per unit area. Because if you remember, capacitance is just epsilon A over D. We're treating this as being a parallel plate. So the area we've already knocked out, and we're just looking at now the per unit area term here. Okay? So this is now the charge that I've got available to me. So the only other term that I need to come up with now is what's the velocity? Okay? So you may have remembered either from 105 or one of these other classes that you've taken. Essentially what's happening is these electrons are getting accelerated by the VDS that we're putting across here. Because that VDS creates an electric field. The electrons feel that electric field, and they get accelerated basically in this x dimension. Okay? So the way you can kind of capture that is we can say that the velocity is going to be some mu, which is the mobility, which is just related to essentially per unit electric field, how fast do things go, then times the electric field in that x direction. Okay? So for those of you who remember, what is this electric field as a function of the voltage that we're putting at any particular point? What's the relationship between electric field and voltage? Yeah, it's the derivative, right? So the electric field is just going to be, I'll just rewrite this whole thing. So the velocity is mu times dv of x dx. Now, when I'm writing these out, I'm playing kind of fast and loose with the signs of things. The charge is actually negative, the velocity is actually negative, but I usually stick with sort of writing things this way because it's easier for me to remember things. And then you just have to keep track of, well, if you get something where you put a voltage across it and current's flowing into that voltage source, you probably got the sign flipped somewhere because that would mean that the device is actually generating power instead of dissipating it. Okay? So now we've actually got essentially all the equations that we need. So, because I've told you what the charge is, I've told you what the velocity is, and again we said that the current is just the charge times that velocity. So now we can just expand that out. And I'm writing this actually, I'm just saying that the drain current is equal to something. Notice these two are both functions of x. But we know just from KCL that the current can't disappear somewhere. So the current has to be constant throughout this x dimension here. Okay? So ID is going to end up being, if I just do the charge first, well, actually I'll do the W, times C aux, VGS minus V of x minus VT, then times the velocity, which is just mu, times dV of x dx. Okay? So now what we're going to do is, and I'll just rewrite that equation that we just did. So we said that ID is W C aux VGS minus V of x minus VT times mu dV of x dx. Well, so now we said that the current has to be continuous as we walk along that channel. Remember, that's the x dimension, and if this is my transistor, so what I'm sort of looking at here is what's the current at each slice here. And we said that that current has to be constant. So if I want to figure out what this really is as a function of the drain to source voltage, well, I can just integrate this expression along the length of the channel. And the simple way to do that is I just take this dx over here, I move it over to the other side, I do ID dx, and then of course equal to all that other stuff that I'm not going to rewrite. And so now what's nice is that on this side over here, we said the drain current is constant. So if I do the integral from essentially, let's say that 0 is the source, and then over to here, that's just the length of my channel. Right? So I'm just doing the integral of that dx. That's just a constant, so it's just going to end up being ID times L. Then on the other side, things are actually also pretty simple because I know that I'm just going from 0 volts up to whatever the drain to source voltage is. So I go from 0 to VDS times W C aux, VGS minus V of x minus VT, dV of x. Okay? So if you just do that integral, you get something that's very kind of nice and easy, which you guys probably all remember, which is just, oh, and then I had the mu over here. So you're just going to get W mu C aux, VGS minus VT minus VDS over 2, all times VDS. Okay, and this is just the simple first order integral that you get from this point to that point. Okay? So how many of you guys kind of remember this equation from 105? Should look familiar, right? Just raise your hand if you kind of remember it. Okay. So this half of the room remembers it and this half of the room doesn't, huh? Haven't taken 105. Okay, got it. How about EE40? You remember from that? No, okay. Well, so if you look at this, what you get is something that, in terms of VDS, you have this VGS minus VT times VDS minus VDS squared over 2. So we have kind of quadratic behavior. So now let's just take a look at this. What does this equation predict as a function of essentially different gate to source voltages and different drain to source voltages? So in some region over here where the VDS is pretty low, well, this VDS squared over 2 term ends up being pretty small. And so this whole thing just kind of looks like a resistor. So if you guys remember, that's called the linear or triode region of operation, where these curves are just pretty, they look almost like a resistor, which is just a straight line. Okay? At some point, what happens is that quadratic term starts to kick in, and this thing basically bends over like this. Now, if I just really took exactly this equation, well, it's a quadratic equation, and quadratic equations like to bend over and go the other way at some point. And what you'd see is a curve that actually started coming back the other way. In other words, I'd increase the voltage on the transistor, and somehow now magically the current would actually start decreasing. So let's take a vote. Who thinks that this is really what's going to happen if I, actually went and measured a transistor? Raise your hand. Okay, who thinks it's not what's going to happen, just so that we're, getting you guys moving? Who has, so you guys have no opinion, huh? Okay. So clearly this is not really what's going to happen. There are some really weird devices you can come up with that'll do something like this, but most of the time if you increase the drain to source voltage on something, guess what? The current is either going to maybe stay the same if you're really lucky, but most likely is actually going to go up a bit. So really this doesn't actually happen, and what that has to do with is that when we were doing our derivation of what the charge was, we basically assumed that we could just write the charge as being VGS minus some V of x minus VT. Well, if V of x ends up being larger than VGS minus VT, that would kind of imply that now somehow we magically have positive carriers moving around. In other words, that somehow we're inverting the sign of this charge group that we're putting in the middle here. Well, that doesn't really happen. What actually happens is that you get this so-called pinch-off, and you sort of have this depletion region that happens at the edge of the channel over there. So if that's what actually happens, then now you get this kind of interesting behavior. This point right here, that's exactly where you have zero charge. In other words, the V of x is exactly equal to VGS minus VT. Okay? So you remember we said that the charge that was underneath the channel, we said that that was kind of linearly related to VGS minus VT, because that's what this equation was coming from. And then we said that the velocity was related to the VDS. But now this sort of effective VDS that we're putting on our channel charge here, that's become constant. Okay? So based on that, what do you guys think is going to happen in terms of the drain current as a function of VGS minus VT? Is it going to look linear? Is it going to look third order? Is it going to look quadratic? What do you guys think? And if you remember from 105, you can go ahead and use that knowledge. Sorry?
It's going to be linear.
Okay, well, so we had two things. One, and I'm asking now actually versus the VGS, not the VDS. So one answer was, and you're actually correct, that if I now look at what happens versus VDS, then instead of this thing coming back down, it'll actually sort of flatten out like that. So this is VDS and this is ID. And that is actually correct. There's some minor things that you have to take care of there, but we'll talk about that again. What I'm actually interested in now is, let's plot the ID versus VGS. Okay? And let's just assume that when you do that, you put the transistor so that the VGS is equal to the VDS. So now what's going to happen? What's that relationship going to look like? Is it going to be sort of, well, we said there was a VT, right? So is that thing going to be linear? Is it going to be quadratic? Is it going to be third order? What do you guys think? Okay, good. Well, you want to use the microphone? It's not going to be exponential. If it was a BJT, it would have been exponential. But remember, we said that there's two things that are important, and somebody over here already said. There's the charge that's important, and there's the velocity that's important. So we said the charge, that was just some capacitance times VGS minus VT. So we've already got something that's linearly increasing with VGS because of this, right? So the charge is linearly going up with VGS. Well, we also said now that the velocity is going to be pinned also by VGS minus VT. So if the velocity is also linearly increasing with VGS, well, I just said that current is charge times velocity, and each one of those was linear on VGS. So, like you said, it's going to be quadratic. Okay? And that's actually exactly what you get if you plug things back in. So you just say that the effective VDS saturates at VGS minus VT. And then if you plug that back into that equation that we just had for the linear regime, you exactly get that the drain current is now proportional to VGS minus VT squared. And again, if you remember absolutely nothing else about NMOS transistors, you should remember that the current is charge times velocity. Because as you'll see in a second, there are actually a bunch of things that make this equation not really true anymore. But if you remember that it's always because of charge and velocity, you'll understand exactly why it is that this isn't working anymore. Okay? Now, when I wrote this equation here, that's this sort of discussion that we just had about if I then drew the drain current versus VDS. This equation is kind of implying that once you get past this VDS is equal to VGS minus VT, it's kind of implying that it's completely flat in this region, like the current's not changing at all. Well, that's not completely true, because you can imagine this is sort of an ideal current source, right, where I can put any voltage across it and nothing changes. Pretty hard to get ideal stuff in the real world. So usually what actually happens is that you get some slight curvature up on that line there. And if you look at the 90 nanometer transistors that I believe you guys are using in the class, you'd actually see that there's a pretty significant curvature here. The reason for that, just in case you guys are curious, it has to do with as I increase the VDS, this region over here keeps increasing in size, and that basically makes this charge go over a smaller effective length. So it just makes it so that the current, instead of being completely flat, has actually some curvature on it. And usually we just model that with some linear extra parameter that we add on to the side there. So instead of it being completely independent of VDS, we get this little lambda extra term here. So does this make sense to everybody so far? Okay. So we've now kind of gotten into sort of three regions of operation. So we started out with the MOSFET was just a switch and it was either on or off. Now we're being a little bit more sophisticated. We're saying, well, if the VGS is less than VT, the switch is off and I get no current. If the VGS minus VT is larger than the VDS, so that you actually have charge all the way from the source over to the drain. This is the source and this is the drain. Right? So in this region of operation, we have this nice continuous channel all the way across here. And we said that in that region, the thing kind of looks like a resistor. And that's where we got this, kind of quadratic looking equation, but only linear on VGS minus VT. Then we said that there was this last region, which usually is called saturation. And it's just called saturation because the current essentially becomes flat in that region. In that one, well, the effective VDS got pinned by VGS minus VT. And so overall, we get this equation that looks like ID is somehow proportional to VGS minus VT squared. And again here in this region, this is the source, this is the drain, and here we have this pinch-off point where you don't actually get continuous charge all the way over into the drain. You just pinch off over here, and then the current just continues flowing through that depletion region. Okay? So if you just go and kind of do a plot, this is the really classic plot of what the transistor behavior looks like. And again, there's sort of this linear region over down in here, where things look pretty much like a resistor. Then as you get the VDS high enough, things start bending over, and then you get a relatively flat amount of current coming out of the device. And if you look at the boundary region between them, that boundary is really just where does VGS minus VT equal VDS? Because that's just that pinch-off point in terms of where the charge goes to zero. Okay? So if you just went into sort of the lab or somehow magically you took apart your laptop and you were able to measure a transistor inside of your microprocessor on your laptop, you'd kind of be very surprised if this is what you were expecting. Because it turns out that modern transistors don't look anything remotely like this. In fact, what they really look like, just skipping this over here. What they really look like is something like this. So in the previous thing, notice there was kind of these quadratic increasing steps as I changed the VGS here. Well, in a modern transistor, as I'm changing the VGS, this thing is just increasing linearly. And if I was to draw that line between where's the sort of saturation region and where's the linear region, what you'd find is that in the modern transistor, that transition happens much, much earlier than you would have expected. The thing's actually going into saturation long before VGS minus VT is equal to VDS. Okay? So what's the culprit, or what's the thing that's changing? Well, there's actually, like we said, there's kind of only two things that can change. It's either the charge or the velocity. Turns out it's the velocity. And the reason for that is actually kind of interesting. So just like when you're out on the highway, if you don't want to get a ticket, there's a certain speed limit you're supposed to obey. Well, guess what? Electrons in silicon also have a speed limit. Now, it's not because they're afraid of getting tickets, obviously. This is a physical phenomenon. What it really has to do with is, atoms are inside of there are actually shaking around at a certain speed. And so if you try and go too fast, you're just very, very likely to hit some atom, and basically it gets you deflected off to some other place. Details are kind of not too important. People like to call this like phonon scattering, just in case you ever hear the term. Bottom line, once you try and go past a certain speed, electrons just flatten out. They can't possibly go any faster than that. Okay? So that says that I can keep on increasing the VDS, which will keep on increasing the field, but the speed at which things go doesn't change. So for a modern transistor, you hit this very, very quickly, and actually you hit it, its very first order in terms of the operation of the transistor. So this speed limit, it's about 10 to the 5 meters per second. So, it's much, much slower than like light, but still pretty fast. And in terms of these sort of critical fields, this is a variable number. I'll kind of tell you what it looks like. So now we have this kind of interesting situation, because down over here, at least for some region, things look a lot like that previous model that we had used, where we just said that the velocity was sort of linearly related to the electric field. But now, once I go past some certain point, I just completely flatten out. Well, so we said that when I was here, the drain current was somehow proportional to VGS minus VT squared. So now, before we do any derivations or anything like that, what do you guys think is going to happen out here? What's the drain current going to be proportional to? In other words, I'm going to have this VGS minus VT here, and let's say it's some, beta here. So what do you guys think that beta is going to be? And let me just give you like a few options. So number 1 is going to be 2, in other words, quadratic. Number 2 will be, let's say, 3, and the first one will be 1. So what do you guys think it's going to be? Who thinks it's 3? 2? 1? Okay, good. You guys are awake. It's going to be 1, right? Because I now have the charge is proportional to VGS minus VT, and the velocity is constant. So if I increase VGS minus VT, only thing that changes is the charge. Okay, this is just showing you kind of the same thing, comparing between the long channel device, but that's exactly what ends up happening. So if you look at this now what's called short channel transistor, and when we say short channel, that really means high electric field, so that you feel this velocity saturation effects. Well, if I move into this short channel regime, once I make the VGS minus VT high enough that I get into this velocity saturation, the current just increases exactly linearly with VGS minus VT. Now, for a long time, this is kind of considered a bad effect, right? Because if I can stay on that quadratic curve, then you could imagine then for the same amount of voltage, I'd actually have much more current. But this velocity saturation, it's kind of stopping me from getting any more current. At least I only have this linear increase now instead of quadratic increase. So from a sort of current per unit micron, this is kind of a bad effect, right? It's slow. It's not giving us as much current as we otherwise might have thought that we would have had. The good news is that if you actually have a transistor that is slightly longer channel length, you actually get more current than you would have thought you originally had. Because now the velocity doesn't really change all that much. And so even though you're changing the channel length, the current doesn't actually drop anywhere near as much. So you're going to see this later on in the class when we start talking about more complex gates. But this is just another reason why we're actually talking about some of these effects here, because you'll see that you'll get some strange behaviors in your circuit that you wouldn't be able to explain without understanding some of these effects that we're talking about here. Okay, so I'm not going to walk through the derivation. It turns out, just like we had done that derivation for sort of the simple linear model of the velocity being mu times e, you can go back and kind of come up with some approximate equation to try and model this saturation behavior. This is one example that very commonly people will use. And I'm not really going to walk through it in too much. They just kind of come up with this so-called critical field, which is, let's say, that, beyond which the velocity essentially becomes constant. And then you have to define some things to get that to be sort of continuous across the boundaries. But again, kind of details are not too important here. You can then use this and go back and kind of redo all that integral. And what you'll end up with is this equation that kind of looks like this. So really, this looks actually very similar to that previous one that we had. Just notice that now there's this extra term here, where if VDS starts becoming really large compared to this E crit L, and remember, E is just an electric field, so times L, that's a voltage. So this is just a dimensionless thing that's kind of normalizing this whole thing. If VDS starts getting really big with respect to this, it's basically going to knock down the amount of current that you get. So just like we had said before, if we used to expect sort of quadratic behavior, now it's going to become more and more linear the larger this effective VDS becomes. Okay? So now if we really look at sort of what our transistors are doing, we almost have this kind of extra region of operation now. So before we just had essentially the linear and saturation regions. Well, now we have still this sort of linear region where when VGS is much larger than VDS. Then once we get past a certain point, the device actually goes into what's called velocity saturation, which is now, this is where the carriers just can't go any faster than they already are. Then afterwards, there's now this sort of normal quote-unquote saturation, which has to do with now really the charge is being pinched off in the channel. Okay? So all this works fine, but we probably want something that's actually kind of even simpler than this. So you can use this equation that I'm giving you here, but you probably, for kind of the back of the envelope calculations, you want something that's even simpler than that. You don't want to kind of really keep track of this extra derating factor here. So what most of the time you're going to end up using is this sort of simplification that I'm going to walk through now. Okay? So the first thing we're going to do is we're just going to assume that instead of having this kind of realistic curving kind of thing here for the velocity, what we're going to do is we're going to say, well, let's just assume that below some critical point, the velocity behaves exactly like it used to. So it's just in that region there. We're just going to assume that the velocity is mu times the electric field. Okay? Then once we get past that critical velocity, then we're just going to assume that it's completely constant at just that Vsat. All right? So this is pretty clearly not reality, because most things in nature don't really like to do these kinky kind of things like that, right? They're usually more smooth and well-behaved, but as we'll see in a second, this is going to let us do a very nice and simple approximation for how the transistor is going to behave. So that's the first approximation we're going to do. The second one is that if you look back at these curves here, where the thing actually saturates kind of varies as you move along here. Well, we kind of don't really want to deal with that. We just kind of want to almost come up with something that once you get past some critical voltage, we're just going to assume that it's velocity saturated. So that's what really this next assumption is going to be. Okay? So here we're just going to assume that once you get past some critical voltage, which is just going to be this critical field here, E crit, times the channel length, we're just going to assume that the actual VD sat is also this E crit L. Okay? So again, this is just an approximation that's going to make our life easier, and I'll show you what this ends up giving you in a second. So the things that now you need to remember is this E crit L, which is just some new VD sat, which is not going to be the same as VGS. Let me do it with a real pen. So normally, maybe if you took 105, you would have normally thought that VD sat is equal to VGS minus VT. Well, now we're just going to redefine this so that sometimes that VD sat is actually going to be equal to E crit L. And I'll give you in more detail kind of which one you're going to end up using. Okay? So if I do that, then I can kind of come up with this slightly simpler model now. So let's first focus kind of on this region's up over here, and then we'll come back to these lower ones. So just like before, we have the linear region where the VGS is much larger than the VDS, and the device looks a lot like a resistor. Then up when we basically pass this sort of fixed line where VDS is equal to VD sat, we're just going to assume that the device is going to end up having, and I'll draw what this is going to look like. Even though you can see the current is still changing here, we're just basically going to assume that this thing is flat now. Okay? So this is our simplified model. The only other thing you have to kind of keep track of is that, well, if you have a low enough VGS on the transistor, you actually don't hit this velocity saturation thing. And so if I don't hit that, then down in this region over here, I'm going to have the exact same characteristics that I used to have from my good old quadratic model. So this is probably sounding a little bit complicated, but turns out that there's a really kind of simple algorithm to use this model now. And this is going to be what's called the unified model. So in most of the problems that you're going to be working with, this is the model for the transistor that you're going to end up using. So to kind of keep the notation simple, I'm just defining here VGT is just VGS minus VT. In other words, it's just how much voltage beyond VT have I put onto my transistor. So just like before, if VGT is less than 0, in other words, VGS is less than VT, I'm going to assume that the switch is off, and I get no current whatsoever flowing through it. Okay? Then once the device turns on, well, I'm just going to always write my current in exactly that old form that we used to have for the linear region. So to kind of simplify things, what I did here is this K prime is just equal to mu C aux. Then this W over L, that's just that same equation that we had from the previous thing. And then here, if you remember, we had the VGS minus VT. And I originally wrote it as minus VDS over 2, that whole thing times VDS. Well, that's all now equivalent to this. The only thing I'm changing now is that instead of this really being VDS, in other words, the real voltage that I put across the transistor, I'm just going to define this as being now an effective VDS. Okay? So this effective VDS is going to be the minimum of 3 different things. It's either going to be the real VDS in the transistor, which is what happens when you're in the linear region, or it's going to be just VGS minus VT, which is what happens when you're in kind of this region here, where you don't actually hit the velocity saturation. Or if I do hit the velocity saturation, it's going to be this VD sat, which we just said was, remember, E crit times L. Okay? And then, of course, I've got this sort of channel length modulation secondary parameter. That one's generally not too important. So now I just always have to remember, essentially, this ID is some scale factor, K, times W over L, times VGS minus VT times VDS, minus VDS squared over 2. And all of the complications about which region of operation and all that, you can just lump that into figuring out what is the effective VDS here. Okay? So at this point, a lot of times people get a little confused and kind of introduced into the new minimum thing. it turns out I could have done exactly this same thing for the original quadratic model and just taken off this VD-SAT. Because what you'd find is if you plugged that in, you'd also find that when VGS minus VT is greater than VDS, you'd say that VDS effective is then just VGS minus VT, which would then lead you back to that very familiar ID as 1/2 K W over L, VGS minus VT squared. Okay, so really all we've done in introducing this new model here is that now instead of just the minimum of VGS minus VT and VDS, you just have to check, well, is the drain to source voltage actually larger than this E crit L? And normally we'll give you that E crit L for the technology. Yeah?
You said if VGS minus VT is greater than VDS, but then the minimum would be
Oh, sorry,
VDS,
VGS
right?
minus VT is less than VDS. No, well, no, okay.
It's
I
just a
confused
little
myself.
flipped, right?
If the VDS is greater than VGS minus VT, the effective VDS that you would choose is VGS minus VT. So in other words, in terms of the velocity term, that's really what this VDS is setting. You always choose the slowest thing that can be, which is always the smallest voltage. Does that make sense now? Okay, good. Other questions? Okay. So if you just go and do a plot of what does that simplified model actually give you versus sort of the real H-spice curves, this is exactly the kind of behavior that you end up with. So again, this line here is just showing the boundaries between the different regions of operation. And you can see it's not that this model is really perfect. It's actually making some mistakes, especially kind of around this region here. But the good news is that most of the time in our transistors, when we use them in digital circuits, we actually basically care about what's the current in the transistor either here or here. Because in digital circuits, most of the time we're not actually sitting around this region here. So even though the model is actually kind of a little bit wrong here, in the regions we actually do care about it, we're pretty much getting the right answer that we're interested in. So really most of the errors in this model, they have to do with this thing that we talked about back here, which was that we assume that this thing is just really a straight line and then bends over like this. Well, if you remember from those curves that we were looking at, the model current does something like this, whereas the real thing does something like that. Well, this extra current that we're getting here is just directly related to this extra velocity that we're kind of assuming that we get when we did this simplification. But again, as long as I don't really care too much about what's going on exactly in that region there, not too big of a deal. Okay. So for the quarter micron process, you guys are using the 90 nanometer this semester, right? Okay, well, so if you're using the quarter micron, then you could actually go and open up the book, and there's this sort of table of parameters that people went and just actually, they did a characterization of what the model ends up looking like for that particular technology. So the numbers obviously are going to be a little bit different for the technology that you guys are working with. So for example, your VT is probably closer to something like 300 millivolts. Your VD-SAT here is probably closer to something like, I'd say roughly 300 millivolts or so. These K numbers, those kind of move around a bit, but that's not too important from your standpoint. Now, there is one thing that's kind of interesting to note here. Let's look at sort of this VD-SAT. And in the slide, there's this V. Let's just call that VD-SAT. Remember, this is just E crit times L. Notice there's this about factor of 2 difference between the NMOS and the PMOS. So why do you guys think it is that the PMOS actually has this larger VD-SAT or larger E crit L? What's happening there? Is the L any different?
mobility of holes is lower than the mobility of
Bingo,
electrons.
exactly. So let's just do a little plot here. So we said that there was this speed limit of the carriers in silicon. So we said that, when I did my simple approximation, let's say that this was for the electrons. So this would be, this slope here would be mu n, right? Well, now let's do that same plot. And so this is going to be ecrit. If we do that same plot for the PMOS transistors, well, the mobility of the holes is actually lower. So what that says is that I actually have to put a higher voltage on that thing in order to hit this velocity saturation behavior, which is exactly why you get this difference in the VD sats here. Because essentially there's just more voltage you have to put in to get up to that same saturated velocity. So as a consequence of that, if you actually look at the IV curves for the PMOS transistor, what you'll see is that if in the NMOS transistor there was really pretty linear steps between the different ranges of VGS minus VT, well, for the PMOS transistor, you can actually see the steps keep on increasing here, right? So the device actually looks still more quadratic, at least it looks more quadratic than the NMOS transistor does. And again, that's simply because the mobility is lower, and so there's less of this velocity saturation effect. Now, on this plot here, there we go. I'm showing everything with sort of negative variables. Just like with that derivation that we had done for the currents, most of the time I actually like to work with everything in sort of absolute values so that I can always just work with things that are positive, and then I just have to remember that for the PMOS, the source is always the higher voltage. So in this example here, I may actually draw something like, instead of ID, I may draw the magnitude of ID, and instead of VDS, I may draw the magnitude of VDS, and then I can actually put the PMOS curves onto the same sort of axis that I do with the NMOS curves, and then I just have to remember that, this thing over here, if it's, let's say, 2.5 volts, what that actually means is that I have a PMOS transistor. Let's say that VGS is also 2.5 volts. What that actually means is something like this, with the current flowing in that direction, as opposed to for the NMOS transistor, the current would actually be flowing into the drain, right? PMOS is actually flowing out of the drain. Okay, any questions on this? So now I can give you like any transistor, and you guys can calculate, which region of operation it's in, and how much current's flowing, and all that other good stuff, right? Okay, good. So you'll definitely be seeing those things in all kinds of homeworks, and as I said, the reason we're doing all this work here is you'll find that this is actually very useful for us to be able to calculate all kinds of characteristics about how the transistors actually end up behaving. So for example, you can use it to figure out, you guys had talked about voltage transfer curves. Well, you can imagine that to figure out what the VTC of an inverter actually looks like, you have to know how much current is flowing in the NMOS transistor and how much current is flowing in the PMOS transistor. So you can basically match them up. Similarly, if you want to know what's the delay through a CMOS inverter going to be, if you guys remember, we had come up with that sort of model where we said that this was approximately going to be a resistor and a capacitor. Well, now that we know how much current is actually flowing through these transistors, we can then actually figure out what is this effective resistance in terms of the delay that we're trying to figure out through this inverter here. Not only that, you can then figure out things like, oh, okay, well, as I scale the technology, do I expect the delay of this thing to improve, to get worse, to stay the same? Because I can then just go and actually see how those different parameters change as I scale the technology, and how that impacts all of these parameters that we had talked about basically in lecture 2 or so. So we're going to end a little bit early here for today. Simone will pick us up next week. Again, if you have any questions, please feel free to come up and bug me.